predicting the pH at the equivalence point of an acid-base titration. Now, do you remember what a titration is? A titration is just a separation of reactants. Put one reactant in the Erlenmeyer flask, put the other reactant in the burette, and slowly add the reactant in the burette until all of the reactant in the Erlenmeyer flask is gone, till it all reacts up. And by knowing the amount of this reactant in the burette that we added and its concentration, we can determine the concentration that was in this container. So it's a very useful and very practical application. It's done, and it's cheap too, so it's done throughout industry in all different types. Our Environmental Protection Agency requires the use of titrations in a lot of environmental analyses. If you're going to make some biodiesel, it looks like you have to do a titration. So what we're going to work on is predicting the pH at the equivalence point of an acid-base titration. So right when you stop adding this burette, right when you stop adding the reactant in the burette and the reaction has gone to completion, what's the pH? So we're titrating an acid with a base. So the weak acid will be in the container, and the strong base will be in the burette. So our acid will be in here, and there will be our base. Okay, so we answered that question. At some point during this titration, the volume of strong base added will be such that the moles of strong base exactly equals the moles of weak acid. So at this point, stop adding that base because the equivalence point is reached. And it's at that equivalence point that we're going to try to predict the pH. So let's get started on this. So here's table 16.1, a list of weak acids. And let's just go ahead and pick one. We'll just pick cyanic acid, HOCN. Name any strong base. Well, let's just pick sodium hydroxide. Assume your chosen weak acid is titrated with your chosen base. As the titration progresses, a conjugate what is produced? So we have HOCN and our strong base. What are we going to make? Water, right? Because that hydroxide will grab onto that acidic hydrogen and we'll make water, but what's left over? OCN minus, right? The conjugate base. When the equivalence point is finally reached, only this conjugate will be present, and it is, well, we already determined that, OCN negative. Since only this conjugate is present at the equivalence point, the solution will be what at the equivalence point? All we have present is that conjugate base. So the solution has to be basic, because all that's present is OCN minus at the equivalence point. All the HOCN is reacted up. What is the chemical equilibrium, i.e. reaction, that controls the pH of this solution at the equivalence point? Okay, before, when we started, the Ka reaction determined the pH because all we had present was cyanic acid. But now at the equivalence point, all we have present is its conjugate base. So what equation will determine it? Our Kb equation. Our Kb reaction is going to determine the pH. And remember how to write Kb reactions? The conjugate base plus water forms a conjugate acid and hydroxide. Predict the equivalence point if 55 mils of a 0.15 molar solution of the chosen acid is titrated with 0.21 molar sodium hydroxide. So our chosen acid was HOCN, cyanic acid. So we're titrating 55 mils of 0.15 molar HOCN with NaOH. What would the equivalence point be? Okay, remember at the equivalence point, at the equivalence point. It's the trick to doing this. At the equivalence point, the moles of hydroxide, right, has to equal the moles of the acid that we're titrating. Okay? It has to equal the same. And what is equivalence point? Equivalence point is what's the volume of this NaOH that I'm going to add. Then where did I stop? Just how much did I add before I stopped adding NaOH? And here's the trick to figuring it out, knowing that the moles are the same. So what do you do with this information? Well, I'd say you just start with something like 55 mils of this. You got to get it into liters. And let's get it into moles of HOCN. In a liter, we have 0.15 moles of cyanic acid. Right, that's what this says. That's what big M is for. And the reaction is 1:1, right? Because we said that there's 1 mole of NaOH for every 1 mole of cyanic acid. So 1 mole of cyanic acid, 1 mole of NaOH. Now our concentration of NaOH so that we can get it into liters than milliliters. So we'll have 0.21 moles of NaOH in a liter. But very often they like to know volumes in milliliters because that's what the bread is in, right? The bread's in milliliters. So in a liter, 1,000 milliliters. What do I get? Everything on top multiply, bottom divide. So 55 divide by 1,000 times 0.15 divide by 0.21 times 1,000, about 39.3. 39.3 milliliters is our equivalence point. So what does that mean? That means that I add exactly 39 mils of this NaOH. Exactly 39 mils. Stop when I've added 39.3 mils. Stop when I've added 39.3 mils, and then the equivalence point is reached. All of that cyanic acid would be reacted. All that's left is the conjugate base. So now predict the concentration of the conjugate formed when at the equivalence point. So what they want to know now is what is the concentration of the conjugate. What was the conjugate? OCN negative. It equals what? Well, it has to equal the moles of OCN minus divided by the total volume. Okay? Well, so it's going to be a two-part problem. The total volume probably will be the easy one because we already did most of the work. We know that we started out with 55 mils of our conjugate acid. So it would be 0.055 liters plus, how much did we add? 39.3 milliliters. 0.0393 liters. So there's my total volume. Now to get the moles of OCN minus, that would just equal the moles of HOCN that I had in the first place, right? Because it's all converted from the weak acid. So let's just find the moles of HOCN and we'll have it. We had, let's clean this up a little bit, we had 55 mils of 0.15 molar. So 0.055 liters times 0.15 moles per liter, and I'll have it. 0.055 times 0.15, 8.25 times 10 to the negative 3. 0.00825 moles. My concentration of that conjugate base is going to be 0.00825 moles all over 0.055 plus 0.0393 liters. Big M. What do I get here? 0.00825 divided by parentheses 0.055 plus 0.0393 close parentheses equals about 0.087. 0.087 molar. Okay? So what we did is we titrated. We had NaOH in our burette. We had HOCN, cyanic acid, in the Erlenmeyer, right? If we added exactly 39.3 mils of that stuff, we reached the equivalence point. And all I had present then, I didn't have HO cyanic acid anymore, then I had OCN minus. And the problem was, what's the pH when I have all OCN minus? What I had to do is calculate the moles, divide it by the liters. And I knew the concentration and volume of the cyanic acid. That's how I got my moles. Divide it by the volume, the total liters. Well, I'll take the initial plus the equivalence point. Okay, so that's the game plan. Let's see if we can do this. So let's see if we can do this. 100 mils of 0.38 molar hydrocyanic acid is titrated with 0.5 molar sodium hydroxide. What conjugate acid or base is formed at the equivalence point, and what is the concentration at the equivalence point? Okay, titrate with a base, you're going to get a base. Titrate with an acid, you're going to get an acid. So for titrating with a base, we're going to get a base. We're starting with hydrocyanic acid, we're going to get what? What's the conjugate base? If you're not sure, you can write it out. All right, this will grab that hydrogen. I'll get water and cyanide. Okay, so that is what we're after. The concentration of cyanide equals what? 2 parts. The moles of a cyanide divided by the total volume. And remember our game plan, the moles of that cyanide, that's the same as the moles of the hydrocyanic acid that we had. And the total volume, well, that's just going to be the initial plus our equivalence point. And make sure it's in liters, and we'll be done. So let's find the moles of hydrocyanic acid first. That is just going to be 0.1 liters times 0.38 moles per liter. Right? I'm getting that from right here. So that part's done. My initial volume was 100 mils, so 0.1 liters. The equivalence point is really where all the work comes in. So let's get that. Okay, and let's stop at liters this time. So what we're going to do, what I like to do, is just realize moles of HCN has to equal moles of sodium hydroxide, and just start with this. Pretty much start with this 100 mils of the hydrocyanic acid and convert that to liters of the NaOH, because that's what I'm after. How much of that NaOH do I have to add? What's the equivalence point? So 0.1 liters times 0.38 moles in a liter of hydrocyanic acid. And then I have 1 mole of hydrocyanic acid for every 1 mole of NaOH. Oh, I have to keep going. And my concentration of NaOH is 0.5 moles of NaOH in a liter. I'm going to stop at liters. And that number, whatever I get, is what I'm going to put in right there for equivalence point. 0.1 times 0.38 divide by 0.5, 0.076. So my concentration of the cyanide is going to be 0.1 liters times 0.38 moles per liter divided by 0.1 liters plus 0.076 liters. Point 0.1 times 0.38 divided by parentheses 0.1 plus 0.076 close parentheses equals 0.216. 0.216 molar will be the concentration of that cyanide at the equivalence point. Write the chemical equilibrium occurring at the equivalence point. Okay, so at the equivalence point, right, I don't have any hydrocyanic acid left. All I have is cyanide. So that's what I'm writing. That's what I'm writing my KB reaction. So add a base, get a base. If that kind of helps you. That helps me remember. Keeps me on track. So to write a KB reaction, cyanide plus water, you always get hydroxide and the conjugate acid. Find the Ka or Kb for the equilibrium that we just wrote. Well, it's a Kb, so Kb, recall, is Kw all over Ka. So it's 1 times 10 to the negative 14 divided by the Ka. And we have to look up the Ka for our conjugate acid, hydrocyanic acid. (4.9 times 10 to the negative 10). 4.9 times 10 to the negative 10. 1 times 10 to the negative 14 divided by 4.9 times 10 to the negative 10, about 2 times 10 to the negative 5, 2.04 times 10 to the negative 5. Extra question. Will the solution be acidic, neutral, or basic at the equivalence point? What dominates at the equivalence point? The conjugate base did. That's why we wrote a Kb reaction. So this had better be a basic solution at the equivalence point. Let's try this again. 250 mils of 0.15 molar ammonia is titrated with 0.45 molar HCl. What conjugate acid or base is formed at the equivalence point, and what is its concentration at the equivalence point? So we titrate with an acid, you get an acid, right? So that means this has to be a base. What is its conjugate acid? If you're not sure, you can write it out. Ammonium. All right, just add an H plus to it. So we want to know, what is the concentration of ammonium? Well, that'll be the moles of ammonia. Well, the moles of ammonium are the same as the moles of ammonia, though, all over the total volume. top part's the easy one, right? Because that has to be the same as the moles of ammonia. So we'd have 0.25 liters times 0.15 moles in a liter. Initially, it's 0.25 liters plus the equivalence point, the volume of HCl that we added, right? Plus the equivalence point, right? And make sure it's in liters. So what volume of HCl do we have to add? What's the equivalence point? Start with the amount of ammonia that you had and convert that to volume of HCl. So start with the 250 mils and convert that to liters of HCl. 0.25 liters of this ammonia, and in every liter I have 0.15 moles of ammonia. All right, I'm getting that just from the concentration here. All these reactions are 1-to-1. For every 1 mole of ammonia, because they're all monoprotic acids and monoprotic conjugate bases, I have 1 mole of HCl. Use our concentration of HCl to get it into liters. 0.45 moles of HCl in a liter. And that number I'm going to put right there. 0.25 times 0.15 divided by 0.45, 0.083. So I can finally get my concentration of ammonia, concentration of ammonium. Concentration of ammonium is going to be 0.25 liters times 0.15 moles per liter divided by 0.25 liters plus 0.083 liters. 0.25 times 0.15 divided by parentheses 0.25 plus 0.083 close parentheses equals 0.1126 molar. Write the chemical equilibrium occurring at the equivalence point. So at the equivalence point, all we have present is ammonium. Okay, conjugate acid or conjugate base? It is a conjugate acid. So you have to write a Ka reaction. So that's always a conjugate acid goes to the conjugate base plus hydrogen ion, right? Ka reaction. Find the Ka or Kb for that equilibrium. So we have to go to our tables. In ammonia, Kb is 1.8 times 10 to the negative 5. So Ka is Kw all over Kb, 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, the Kb for ammonia. 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, about 5.5, 5.6 times 10 to the negative 10. And will this solution be acidic, basic, or neutral at the equivalence point? It'll be acidic because it's a conjugate acid at the equivalence point. So our big goal is to determine the pH at the equivalence point. Now, we haven't got quite there yet. We're halfway there. We're going to spend the next class period on wrapping this up. But this is the hard part. We are determining the concentration of the conjugate acid or conjugate base that's present, that's dominant at the equivalence point, right? And how do you get it? First, you figure out what it is, and then you divide the moles by the total volume. And the total volume is always what was there initially plus the equivalence point.